Thanks for inviting me. I had the good fortune of spending an entire career working on sea otters from Southern California to Russia. And I'm pleased to share some information that I gained over that time that might be useful in your deliberations regarding reintroductions of sea otters to Oregon coast. So I'm going to start, and I'm going to focus on my presentation with some of the biology and natural history of sea otters that might be relevant to reintroductions and the issues surrounding the return of sea otters to their historic habitat. This is simply a plot of the average annual harvest of sea otters over about a 160-year period. You're going to focus on kind of the variability in that harvest over time. And these are annual harvests, but they're not in, these are 10 to about 10-year blocks of time. So essentially, this represents the harvest of about 700 to 900,000 animals over a 150-year period. And with an average harvest of about 5,000 to 6,000 animals a year. But this resulted in the near extirpation of this species. But this harvest rate was only about 2% on an annual basis. And I want to pose the question of why wasn't that sustainable? We know from today, from the reproductive rates and the mortality rates of this species, that they should be able to sustain a harvest significantly higher than this 2%. Well, one of the answers to that question lies in the small home range that sea otters exhibit. And here's a simple plot. These bubbles represent the annual home ranges of 26 different sea otters from southeast Alaska. And basically the point is here is that the average annual home range of these animals are on the order of single digits to maybe 20 or 30 square kilometers. Not much more than a handful of square blocks. So an exceedingly small home range for a large mammal. And this strong fidelity, this small home range, results in structuring of sea otter populations at very small spatial scales. I'm going to try to demonstrate that as I proceed. But this attribute of their biology is one of the factors that led to their serial depletions and extinctions during the fur trade. And it also contributes to the high loss of sea otters during the translocations. And we've seen that throughout any translocation that's taken place. So I'm going to talk about sea otters in southeast Alaska first. 403 sea otters were translocated to southeast Alaska over a 5-year period in the late 1960s. Here's a map of southeast Alaska that shows the 6 translocation sites. 2 of those in southern southeast Alaska, down down at the southern part of the range there at the Morel Islands and the Barrier Islands, and then 4 translocation sites in the northern part of southeast Alaska. And here's the numbers of animals that were translocated. Basically, about 100 animals were moved to southern southeast Alaska and about 300 to northern southeast Alaska. So then these weren't evenly distributed, and almost half of the animals were translocated to Cass Bay, which is interior to the other translocation sites. It probably has some relevance to the success of this translocation. In 2012, there were 25,000 sea otters, or about 20% of the global sea otter population occurred in southeast Alaska. And that number, if the rate of increases continued, probably is around 40 or 45,000 animals today. So this has been hugely successful with an average growth rate of about 12%. Now, I'm going to caution you that growth rate, I'm going to show you that growth rate can be a bit misleading. So why was this translocation so successful? Well, in my view, it's because, one, there was lots of animals translocated. They were translocated over a 5-year period, and they were distributed amongst a broad number of sites throughout nearly 500 kilometers of coastline in southeast Alaska. And probably equally important is they were introduced into healthy habitats. One of the good things about the fur trade was that although they killed lots of animals, they really didn't destroy the habitat. The coastal marine habitats of Western North America remained in pretty good shape. And in fact, because of the absence of sea otters for long periods of time, the prey populations were probably exceeded what they might be when sea otters are at an equilibrium density. So we're going to look a little bit at the distribution of animals in Southeast Alaska and the variation in the growth rates within Southeast Alaska. So this is southern Southeast Alaska, where there was only 100 animals introduced, roughly. 2002, there were about almost 6,000 animals, and they doubled to nearly 13,000 animals in 2010, with an average annual growth rate of about 13%. In northern Southeast Alaska, where the bulk of animals were released, in 2002 there was just slightly less than 2,000 animals, and they approximately doubled over a 10-year period, with an average annual growth rate of about 5%. I'm going to look at Glacier Bay, which is an area that is in the northern part of northern Southeast Alaska. Animals didn't occur here until 1993, but by 2002 there was about 1,260 animals there. In 2012 there was 9,000 animals there, and this is an average annual growth rate of about 46%, which far exceeds the intrinsic potential growth rate of this species. So clearly there was immigration into this area that was supplementing their reproduction to account for this type of growth rate. So in summary, here's what kind of the Southeast Alaska growth rates look like. Overall, it's been about 12% a year, although early on the growth rate was much higher than this. Southern Southeast Alaska, 13%. Northern Southeast Alaska, 5%. Port Althorpe, a place that we did some research quite a few decades ago, essentially has been stable for the past 20 years. There hasn't been much change. At the southern end of the northern population, there's been slight growth at about 5% a year. But you throw in Glacier Bay and you end up with an average growth rate overall of about 12% in Southeast Alaska. So this demonstrates one of the scales that populations are structuring themselves in terms of demographic rates, births and deaths, that result in these growth rates over time. So clearly there's not a single population. There's probably 40,000 animals here now, but it's not a single population. And recent work conducted by Tim Tinker and myself suggests that there may be as many as 30 distinct populations, demographically distinct populations within Southeast Alaska. So that's a kind of an important consideration regarding the introduction and subsequent growth of sea otter populations. So I'm going to talk now about empirical data used to describe the effects of sea otters on soft sediment ecosystems in Glacier Bay. So we took advantage of the absence of sea otters in the early 1990s by establishing a large number of sites where we could monitor the state of the system, the benthic invertebrate populations in particular, the algal populations, before sea otters moved in there, with the expectation that someday they would. And fortunately for us, sea otters moved in shortly after we established these situations. But these are very different than the rocky habitats that we've heard about thus far today, in that most of the invertebrates occur, they're in fauna, they're buried in the sediment. There are things like clams, a variety of different types of clams, and some other worms, and a variety of different species. But foraging in this habitat is different than it is in rocky habitats, because it requires sea otters to basically excavate large amounts of sediments to get to their prey. So there was 3 study components that we implemented in 1991, and these include monitoring sea otter abundance over time and their distribution within Glacier Bay, looking at sea otter diet over time, and looking at their prey populations and the structure of the community over time. And I'm just going to give a few examples of some of the results that we've gotten. This study is ongoing because we're continuing to look at the role of sea otters in structuring these communities. So this is the distribution of our study sites. There's about 90 of them scattered throughout the bay. Some of them are intertidal, some of them are, and the others are subtidal. And this was what the sea otter distribution looked like in 1993. Just a little bubble at the mouth of Glacier Bay. And about 20 years later, this is a heat map looking at the density of sea otters within Glacier Bay. And so you can see that there's some of our study sites that have been influenced by sea otters at a high level. There's sites that have been influenced at a lesser level, and there's a large number of sites that haven't been influenced at all or hadn't been in 2012. So this gives us a powerful experimental design to actually assign cause to changes that we might detect. One of the great things about sea otters is, as a carnivore, is that you can watch them prey, and you can quantify, you can identify what they're eating, you can quantify what they're eating, you can look at the number of prey that they're eating, and you can measure the relative size of what they're eating. And so this forms an important part of understanding what the role that they play is in structuring systems. So this just looks at sea otter diet through time, and essentially 80 to 90% of their diet consists of clams, and a variety of different species of clams. The green sea urchin, which is a different species of urchin that we've talked about and we've heard about earlier. And then this other one is a mussel, and this is a horse mussel. It's Modiolus. It's a very large mussel. I'll show you a picture of the size of this animal. But probably more important than the diet, or equally as important as the diet in terms of the sea otter and the population and the status of their population, has to do with the amount of energy that they intake on a daily basis or on an hourly basis. And in this case, it's on a minute basis. So this plot shows energy intake rates on the left side in the early stages of reoccupation. And animals there were getting about 18 or so kilocalories per minute of energy. And as they continue to occupy habitat, continue to forage, they are reducing the amount of available prey, and that's reflected in declining amounts of energy intake rates. And we know from this type of work, which is being conducted throughout the sea otter's range, that once they get down kind of in those single digits, they're approaching kind of the maximum amount of time that they can allocate to foraging. And at a time then when the population is at or near an equilibrium with their available prey. So it's an important aspect to consider in terms of monitoring the status of population. So here I'm going to give you 3 examples of the effects of sea otters, the direct effects of sea otters on some of their prey. And the first plot is the density of horse mussels. The red bars are the density of horse mussels, the number per meter squared prior to sea otters occupying Glacier Bay. They range, they average around 100 to 200, but at densities as high as 300 per meter squared. After sea otters had been there for a decade, essentially these mussels were gone. There were very few of them still at these study sites. So a very strong direct effect of sea otters on horse mussels. It's a little bit different picture when we look at the biomass of subtidal clams. And again, this is a variety of different species. But 4 of the 7 sites that I have pictured here, we saw significant declines in the biomass of subtidal clams following occupation by sea otters. And at the other sites, we basically didn't see any change. So a little bit different picture than the Modiolus, likely reflecting kind of prey preferences and the ease of access to various types of prey, and the energy that's required to excavate large amounts of sediment. And then finally, we're going to look at the biomass of clam in the intertidal. And I'll go back up a second. So you can look at these biomass estimates were on the order, of 1,000 to upwards of 2,500 grams per quarter square meter. When we look in the intertidal, we have maximum values up there around 300. So a much lower density of biomass of bivalves in the intertidal sites. And these red bars represent biomass of the edible biomass of clams prior to sea otters. And along the x-axis, or the bottom line, we have areas where sea otters have not occurred, or did not occur as of 10 years post colonization, where they occurred at low densities, moderate densities, and high densities. And we can look at where sea otters didn't recolonize. They didn't recolonize areas where clams' biomass was low. We didn't see any change in that biomass over time. And where sea otter densities were low, again, there was basically no change. Two things I would conclude from this. One of them is that otters are not moving into areas where prey densities were low, and subsequently they weren't having much of an effect on those prey densities. But when we looked at areas where sea otter densities were moderate or at high, we saw significant declines in the biomass of these species of intertidal clams. So there's a number of other fisheries that are potentially impacted by sea otters in Southeast Alaska. And there's much of the understanding of direct effects of sea otters on prey populations is anecdotal. We don't often have these types of data to really quantify what the impacts of sea otters are. You'll find a variety of different opinions about what that might be, but I think it's important to recognize that some of it has quantitative data and others don't necessarily. But these other fisheries might include things like Dungeness king and tanner crabs, the pinto or northern abalone that we heard about earlier, a variety of species of urchins, cucumbers and geoduck clams, and I referenced some work that's recently been published that indicates an impact by sea otters on those two species, and also razor clams and a variety of different shrimp that support both commercial, recreational, and subsistence fisheries. I'm going to talk just briefly about kind of potential mitigation of some of these adverse impacts. Examples include oyster farms throughout much of Southeast Alaska and in the Gulf of Alaska that provide an alternative perhaps to some of these fisheries that may be impacted adversely by sea otters. And also about refugia. So, and I'm going to talk, speculate about Dungeness crab in particular, because most of the fisheries that occur on Dungeness crab occur in relatively shallow water. But prey populations that extend their range beyond the foraging depths of sea otters provide at least the potential for a refugia that might be exploited post-sea otter recolonization. And here's a plot of the foraging dive depths of sea otters in Southeast Alaska. The pink bars are females, the blue bars are males. And essentially what you can see is that there's very, very little foraging that takes place beyond 60, 65 meters, or about 200 feet of depth. They are capable of feeding out to about 300 feet, but relatively little foraging takes place beyond 200 meters. And by females, 30 meters or so is kind of the upper distribution of their foraging depth. So this provides at least the opportunity for fisheries that provide, or depths that provide a refuge for prey species beyond the capabilities of foraging sea otters. Crevice habitat that we heard about earlier for abalones provides another example. I want to talk briefly here about some of the benefits of sea otters in Southeast Alaska. Clearly the species conservation, the recovery, the translocation was hugely successful in terms of conserving sea otters in Southeast Alaska. Ecosystem restoration. Primary productivity being one of the principal benefits of recovering sea otter populations. And it's not necessarily exclusively in canopy forming kelp species, which are visible to humans from the surface. But there's a huge understory, and you saw some photos of it earlier, a variety of different species that provide a large amount of primary productivity in the system. And that includes the kelps, the various different algae other than the kelps, and the seagrasses. And then the indirect effects. And it's been fairly simple to look at the direct effects of sea otters, but the indirect effects are complicated. And you saw some great examples about documenting what those are. And you heard about how those indirect effects can be much more challenging to understand because of the dimensionality of those. They can go in so many different directions, and trying to anticipate those can be difficult. In Southeast Alaska, there's been a subsistence use of sea otters, and this is for skin sewing practices, and it falls under the exemption that the Native Alaskans have to the Marine Mammal Protection Act. But there's an industry now in Southeast Alaska that's utilizing sea otters. And most recently, it appears as though there's been some success in managing sea otter populations at fairly small spatial scales to encourage the recovery, the restoration of important invertebrate species, culturally important species that were used for food or other purposes historically. And that's allowed because of this exemption that allows the harvest of sea otters. And of course, there's other economic opportunities, things like wildlife viewing opportunities and things of that nature. And that's all I have on Southeast Alaska. Thanks for your attention to that.